discuss about the advantages of this process. So it's relatively very rapid, or you can say a very quick process as compared to the your other you can say additive and subtractive manufacturing process. It's very quick, and in very short time period you can obtain a very finished product. So it is very, you can say, supportive for the mass production, and you obtain near net shape parts. We have already discussed about near net shape manufacturing somewhere in our previous classes. If I remember that, I have already explained you what is near net shape manufacturing. So once again, I am telling you that near net shape manufacturing is a manufacturing in which the parts are obtained of a very high quality and very high surface finish, and you don't require further machining and further sizing and other treatments to make it into a useful product. So this is a process which facilitates the mass production, and very you can say very efficient, and you can say very little amount of material is wasted in this process, and about 97% of the starting powders are converted into your useful product. Only 3-4% or 5% maximum powder is wasted while handling and while transferring the powders into the mold cavity. So basically in the mixing chamber we mix the powder, and then we transfer this powder into the die cavity with the help of the powder feeders. So while pouring into the powder feeder, there are chances that you can use 1 or 2% of the powder while pouring if your process is not automized. And from a powder feeder to the die cavity, sometimes some powder particles also stick inside the powder feeder. So but in the next lot, or if you want to change the part, and if you want to change the material, you have to take out that used powder which is sticked inside, which has stuck inside the powder feeder. So from there only 3 to 5% of the powder wastage is observed, and then you can obtain complex shape parts, the parts which even very difficult to make with the help of castings and with the help of machinings. And you also know that in machining you required a sophisticated machine tool, and also a sharp cutting tool of different geometries, and hard materials are difficult to cut, and the materials which have high melting points are difficult to melt, and then it is very difficult to cast them into useful products, such as one of very do you know that tungsten filament, which is used in the bulbs, light bulbs, they are also produced by this powder metallurgy. So you know that tungsten is a very hard material, is also a very high strength material, and drawing into wire is also a very difficult process, and then cutting and all finishing process is also very difficult for the tungsten. So I request you to go through the books, and to also to search the internet that how tungsten filament is formed with the help of powder metallurgy process. So this is very good example, and certain metal alloy combinations and cermets can be formed by powder metallurgy that cannot be produced by other methods, just like in casting. So in casting, you all know that you can make a product of any metal, any alloy, or even the, you can say, ceramic or cermet composition. But you all know that in casting, the high temperature results in basically the development of unwanted phases, unwanted microstructure. So basically there is a problem with different type of you can say different types of different problems are also encountered while casting of the products, like porosity is there, like change in the microstructure is there. But here in this technique, you all know that we are all working below the melting point of a material, so such problems are very less observed in this case. And up to now, in our previous classes, we have always discussed that porosity is a very you can say it's undesirable. It's undesirable in the mechanical components, but but in some advanced applications, like in the tribological applications, which is basically, tribology is basically the study of friction and wear. The tribological components like bearings, ball bearings, or some components which have a sliding motion between them. So there, you can say the porosity is beneficial. Porosity is beneficial, first of all, in the case of making filters. You all know that filters are porous, and due to the specific porosity, pore size, and their distribution, or you can say their configuration, you are able to filter out your desirable fluids from them. And another application is the oil impregnated bearings. The oil impregnated bearings are very special type of bearings in which we intentionally create the porosity. Okay, and what is the application of this porosity? So basically, what it does, it holds the lubricant in the pores. It holds the lubricant in the pores, and whenever these bearings are compressed in the loading conditions, so automatically the trapped lubricant, it comes out from the pores and it causes the automatic lubrication. So this is a very brief discussion about the oil impregnated bearings or oil impregnated bushings. You can learn a lot of things on the internet, and I will try to share different videos with you. And as I have said that this is a near net shaped manufacturing process, so close tolerances can be achieved. You can say a very tight tolerance can be achieved, and in general, you can say in general routine, plus minus 0.13 tolerances can be easily achieved without any problem, any problem. And the process can be totally automated, so you don't require any human intervention. Just you take raw material from the supplier, and then just you put all the raw material in on a conveyor belt, and this conveyor belt, first it feeds the powder into the mixer, and from their mixture, it pours the powder, mixed powder, into the powder feeder, and from their powder feeder, it pours the powder feeder, or it basically sends the powder through flow tubes into the die cavity, and from their die cavity, automatic compaction will takes place, automatic ejection of the part takes place, and from there, automatic transfer of the compacted part on again onto the conveyor belt, and from that conveyor belt it goes to the sintering furnace, and in the sintering furnace it automatically gets sintered, and at the other end you get the finished part. We'll discuss about the disadvantages. So disadvantages, as I've told you that this is a process which can be easily automized. So the tooling and equipment costs are initially very high, but with the course of time and with the mass production, you can compensate with the profit which you will get after the product is sold to the market. So only with the help of mass production and with the low rejection, you can earn the profit, and then you can bear the tooling and equipment cost. But initially the setup is very costly. Also know that metallic powders, as compared to the solid metallic, you can say the raw material, the metallic powders are expensive, and they are it is very difficult to store them. It is very difficult to store them and to handle these metallic powders, because you all know that as the metal powder, in case of metal powders, they are readily oxidized. Metals have the tendency of oxidize. Even you take a raw material in the solid form, a big ingots you have, if you keep them for a long time without using them, they will definitely, they will be oxidized. But in case of the metal powders, they are easily oxidized. Okay, so they have a degradation with the course of time, and metal powders are, you can say, this is pyrophoric in nature. The metal powders are widely used to make the firecrackers because they have a very large surface area and then can easily catch fire. Okay, so magnesium powder is an example which we use to make the firecrackers. And magnesium is very flammable in nature, and particularly all materials in a very fine particle size, they can easily catch fire. Okay, so there are limitations on the part geometry because metal powders do not readily flow laterally in the die during the pressure. So sometimes, basically, it's a very important to consider the powder particle size and powder particle shape. Okay, so the powder particle size should be so defined that it should facilitate your compaction, and also the powder particle shape is also a very big factor which governs its flow into the die cavity during the pressing. So sometimes it happens that the powder should it is a very important requirement that your powder should flow freely inside the die cavity during the pouring as well as during the pressing. So consider the case when the powder is not flowing efficiently into the die cavity and you are applying pressure on the this powder mass. Though what happens that at some place the powder get consolidated at different location, it will still be in the powder form. So such parts on ejection from the die will fail, definitely it fail. Okay, and during the consolidation they have the tendency to stick to the die cavity as well as the upper and the lower punch. So therefore the allowances must be provided for the easy ejection of the part from the die after the pressing. So you have to very effectively think on the part geometry as well as the die design and the selection of the die material and the punch material. So these are different, you can say, parameters which you have to study in the R&D stage, research and development stage, basically in the part development stage. Okay, and variation in the material density throughout the part, it is a very big problem, especially for the complex part geometry. So suppose there is a case when you have a you can say you have a die and punch arrangement, and you have poured or filled your die into the you have poured your powder into the die cavity and you have pressed. So now consider the case that the force will not be effectively transferred from the top portion of the metal powder layer to the bottom portion of the this metal powder layer. So whatever the powder which is very close to the punch surface, it has more density as compared to the powder which is beneath the successive layers. So this is the problem with the powder metallurgy